Every year, our planet is struck by lightning more than 1 billion times. Some flashes illuminate vast tropical rainforests. Others dance silently across empty oceans where no human eyes ever witnessed them. Storms roll over mountains, deserts, grasslands, and cities, sending brilliant streaks of light across the sky before disappearing just as quickly as they arrived. For thousands of years, lightning inspired both wonder and fear. Ancient civilizations believed these blinding flashes were weapons wielded by gods. The Greeks imagined Zeus hurling bolts from Mount Olympus. In Norse mythology, the rumble of thunder was said to be the mighty hammer of Thor echoing across the heavens. Nearly every culture throughout history created its own stories to explain these sudden explosions of light. Even today, lightning still feels almost supernatural. It appears without warning. It moves faster than the eye can follow. It briefly turns night into day before vanishing once again into darkness. Yet despite seeing it our entire lives, most of us have never stopped to ask one surprisingly simple question. Where does lightning actually come from? Does it begin inside the clouds? Does it fall from the sky? Or has it been there all along, quietly waiting for the perfect moment to appear? The answer takes us on an incredible journey high above the earth, into towering storm clouds where billions upon billions of tiny droplets of water and fragments of ice are constantly colliding in an invisible dance. Hidden inside these clouds is one of nature's most extraordinary electrical machines. A machine capable of generating hundreds of millions of volts, heating the air to temperatures nearly 5 times hotter than the surface of the sun, and releasing enough energy in an instant to light up the entire horizon. But strangely enough, lightning doesn't begin with electricity. It begins with sunlight. Our story starts on a warm afternoon, long before dark clouds gather overhead. The sun has been quietly warming the Earth's surface for hours. Lakes shimmer beneath its light. Rivers flow steadily toward the sea. Oceans stretch across nearly 3/4 of our planet, absorbing enormous amounts of solar energy every single day. As the sunlight warms the surface of the water, something remarkable begins to happen. Individual water molecules, once bound together in liquid form, gain enough energy to escape into the air. One by one, they leave behind the surface below, becoming invisible water vapor that rises gently into the atmosphere. This process, known as evaporation, is happening almost everywhere, almost all the time. Every ocean, every lake, every river, even the moisture clinging to leaves after an early morning rain slowly returns to the sky. Plants join in as well. Through tiny openings in their leaves called stomata, they continuously release water vapor into the atmosphere in a process known as transpiration. Together, evaporation and transpiration quietly lift trillions of gallons of water into the air every day, forming an endless cycle that has shaped our planet for billions of years. Although we rarely notice it, the air around us is never truly empty. It carries invisible water almost everywhere we go. As this warm, moisture-filled air rises higher into the atmosphere, something begins to change. The higher it climbs, the colder the surrounding air becomes. Without enough warmth to remain an invisible gas, the water vapor begins gathering around microscopic particles drifting through the atmosphere. Tiny grains of dust, specks of sea salt carried inland by ocean winds. Even pollen or smoke floating high above the Earth can become the foundation for something much larger. Around each of these nearly invisible particles, water begins to collect. At first, the droplets are unimaginably small, so tiny that millions could fit inside a single raindrop. Floating together, they create what we recognize from the ground as a cloud. Most clouds are peaceful places. Soft, gentle, almost weightless. They drift wherever the winds carry them, painting changing shapes across the sky while quietly reflecting sunlight back into space. But every so often, the atmosphere begins preparing for something much more dramatic. Far below, the sun continues heating the ground. Fields, forests, roads, and rocky hillsides all warm at different speeds, creating great columns of rising warm air. Meteorologists call these rising currents updrafts, and on particularly hot, humid days, they can become astonishingly powerful. Instead of allowing a cloud to drift peacefully across the sky, these invisible elevators of warm air begin pushing it higher and higher, until an ordinary cloud starts transforming into one of the tallest structures found anywhere on Earth. The invisible elevator of warm air continues lifting the growing cloud higher and higher into the sky. At first, the transformation is almost impossible to notice from the ground. The cloud simply appears a little larger than it was a few minutes ago. A little taller, a little brighter around its edges where the afternoon sun catches fresh towers of billowing white vapor. But several miles above the Earth, an extraordinary construction project is quietly underway. Every second, thousands of tons of warm, moisture-filled air are being carried upward, feeding the cloud from below like an enormous chimney that never stops growing. Soon, what began as a harmless puff of white has become something altogether different. Meteorologists call these giants cumulonimbus clouds, though many people simply know them as thunderheads. They are among the tallest structures in Earth's atmosphere. On particularly powerful days, they can stretch more than 60,000 feet into the sky, climbing higher than commercial airplanes and reaching the very edge of the lower atmosphere. If you could somehow place Mount Everest beneath one of the largest thunderstorms, its summit would still fall thousands of feet short of the cloud's towering peak. Yet despite their immense size, these giants are built from something remarkably delicate. Water. Or perhaps more accurately, water in every form imaginable. Near the bottom of the cloud, where temperatures remain relatively warm, countless droplets of liquid water drift effortlessly through the rising air. Higher up, where the atmosphere grows colder with every passing 1,000 feet, those droplets begin to freeze. Tiny ice crystals form alongside partially frozen pellets known as graupel, while larger pieces continue growing into hailstones that are carried upward again and again by the cloud's powerful updrafts. Some hailstones become so heavy that gravity briefly wins, pulling them downward before another surge of rising air catches them once more and carries them back toward the freezing heights above. Inside the cloud, it is anything but peaceful. While the cloud appears calm from miles away, hidden within it is a constant storm of motion. Tiny ice crystals race upward on invisible currents. Heavy graupel tumbles downward through swirling winds. Water droplets freeze, melt, and freeze again as they travel through layers of dramatically different temperatures. Every second, countless particles collide with one another in every direction. Some impacts are so gentle they barely disturb the drifting ice. Others happen at speeds approaching 60 miles per hour, sending frozen fragments scattering through the cloud like microscopic fireworks. If you could somehow shrink yourself smaller than a grain of sand and step inside this enormous thunderhead, you would find yourself surrounded by a world unlike anything humans have ever naturally experienced. Brilliant shafts of sunlight would occasionally pierce the cloud before vanishing into darkness again. Winds would rush past from multiple directions at once. Tiny droplets would appear suspended in midair while chunks of ice larger than your hand hurtled upward beside them. The cloud would feel less like floating through mist and more like standing inside an endless, swirling snowstorm where gravity itself seemed uncertain. And all the while, something invisible would slowly begin to change. Every collision between those tiny pieces of ice carries more than simple motion. It carries electrons. Electrons are among the smallest building blocks of ordinary matter. Every atom in your body, every grain of sand on a beach, every tree, every mountain, every drop of rain contains them. Normally they remain balanced, quietly orbiting the nuclei of atoms without drawing much attention to themselves. But under the chaotic conditions inside a thunderstorm, that balance begins to break. Scientists spent decades trying to understand exactly how this happens. Even today, researchers continue refining the details, but the overall picture has become increasingly clear. When lightweight ice crystals collide with larger pieces of gravel inside the freezing middle layers of the cloud, tiny electrons are transferred from one particle to another. The exact direction depends on temperature, size, and the conditions of the collision, but over millions upon millions of impacts, a remarkable pattern begins to emerge. The smaller, lighter ice crystals tend to become positively charged. Because they weigh so little, the cloud's powerful updrafts carry them ever higher toward the towering summit of the storm. The heavier gravel and hailstones, now carrying an excess of negatively charged electrons, struggle against gravity. They drift downward into the lower portions of the cloud where the rising air is no longer strong enough to support them. No single collision accomplishes very much. One tiny transfer of electrons is almost meaningless. Even 1,000 collisions accomplish almost nothing. But thunderstorms are astonishingly patient. Inside a mature storm, these microscopic encounters happen not by the thousands, nor by the millions, but by numbers so vast they become almost impossible to imagine. Billions of collisions become trillions. Trillions become quadrillions. Hour after hour, the cloud quietly sorts electrical charge with extraordinary efficiency, almost like an invisible factory assembling one tiny piece at a time. Slowly, almost imperceptibly, the entire cloud begins to organize itself. Its upper reaches become filled with positive charge. Its lower half grows increasingly negative. Without making a sound, without producing even the faintest flash of light, the thunderstorm has transformed itself into one of the most powerful natural batteries on Earth. And below it, something equally remarkable has begun happening to the world beneath the storm. The ground itself is starting to respond. Meanwhile, far below the towering storm, the landscape remains blissfully unaware that it has become part of an invisible electrical experiment. Trees continue swaying gently in the warm breeze. Rivers flow as they always have, winding patiently toward the sea. Birds glide beneath the darkening clouds, searching for shelter as the afternoon grows strangely quiet. To anyone standing on the ground, It simply feels as though a storm is approaching. The air becomes heavier with humidity. The sunlight softens behind thickening clouds. A cool gust of wind announces that rain is not far away. But hidden within every blade of grass, every rooftop, every mountain peak, and every person beneath the storm, billions upon billions of tiny electric charges are beginning to shift. The negatively charged base of the thundercloud exerts an invisible influence on everything below it. Like the opposite ends of two magnets, electrical charges naturally respond to one another. As the storm grows increasingly negative, electrons within the Earth's surface are gently pushed away. They travel deeper into the ground or spread outward across the landscape, leaving behind an excess of positive charge near the surface. No sparks leap through the air. No visible glow surrounds the trees. The entire process unfolds silently, completely hidden from human eyes. It is as though the storm and the earth have begun an invisible conversation. The cloud presses downward with an ever-growing electrical force. The ground quietly answers back. For every second that passes, the difference between them grows larger. Scientists refer to this as an electric field, but the phrase hardly captures the extraordinary scale of what is happening. Across a single thunderstorm, the electrical potential can climb into the hundreds of millions of volts. It is an amount of energy so immense that our everyday experiences with electricity scarcely provide a useful comparison. The static shock you might feel after walking across a carpet during winter measures only a few thousand volts. Enough to surprise you, perhaps even make you jump, but harmless because it carries so little energy. A mature thunderstorm exists on an entirely different scale. It patiently stores energy for minutes, sometimes even hours, without releasing it. Imagine stretching a giant rubber band. At first, very little changes. The band offers only gentle resistance. But as you continue pulling, more and more energy becomes trapped within it. Every additional inch stores a little more tension until eventually the rubber can stretch no farther. At some point, something has to give. A thunderstorm behaves in much the same way. The collisions inside the cloud never stop. Tiny ice crystals continue exchanging electrons with Graupel. The upper cloud becomes more positive. The lower cloud becomes increasingly negative. The electrical tension between sky and earth grows stronger and stronger, almost as though the atmosphere itself is being stretched beyond its limits. And yet, the air between the cloud and the ground seems to prevent anything from happening. This may seem surprising because we often think of air as empty space, but in reality it is an extraordinary insulator. Every breath you take contains trillions upon trillions of molecules, mostly nitrogen and oxygen, packed closely enough together to prevent electricity from flowing freely. Under normal conditions, dry air does an excellent job of keeping electrical charges separated. Without this invisible barrier, every thunderstorm would discharge almost immediately, never allowing enough energy to accumulate for the brilliant flashes we see. In a sense, the atmosphere acts like the walls of an enormous dam. Behind those walls, electrical energy continues building. The dam holds. For a while. But no barrier is perfect forever. As the electric field strengthens, individual air molecules begin experiencing forces they were never meant to withstand. Electrons, normally held securely within their atoms, become increasingly unstable. The air itself is approaching a breaking point. Scientists call this electrical breakdown. For countless generations, people believed the bright flash of lightning was the beginning of the event. It certainly looks that way. One moment the sky is dark, and the next it explodes with brilliant white light. But modern high-speed cameras, capable of recording hundreds of thousands of frames every second, have revealed something astonishing. The lightning we see is actually the end of the story. Long before the brilliant flash appears, something almost invisible begins descending from the cloud. It is called a steppe leader. Unlike the dazzling bolt that follows, a steppe leader is incredibly faint. Human eyes cannot normally see it because it emits only a tiny fraction of the light produced by the main strike. It moves downward in short, jagged bursts, advancing perhaps a few dozen yards before briefly pausing, then branching again in several different directions. For millionths of a second it hesitates, almost as if searching. Then it chooses another path, weaving unpredictably through the atmosphere. To early scientists, its erratic path was baffling. Why doesn't lightning travel in a straight line? The answer lies within the invisible world of the air itself. No two parts of the atmosphere are exactly alike. Tiny differences in humidity, temperature, dust, smoke, pollen, and even microscopic pockets of ionized air create easier and harder routes for electricity to follow. The steppe leader is not choosing randomly. It is constantly probing, testing countless possible paths through the sky, always seeking the one that offers the least resistance. It is less like an arrow fired toward the earth, and more like the roots of a great tree growing through soil, slowly branching outward in search of the easiest way forward. With every tiny step, the invisible path extends closer to the ground, closer to the forests, closer to the fields, closer to rooftops, mountaintops, lakes, and lonely trees standing beneath the storm. The distance separating the cloud from the earth is shrinking with astonishing speed. And somewhere below, the ground is preparing to answer. The moment the invisible steppe leader reaches within a few dozen yards of the ground, something extraordinary begins happening below. The earth, which has spent the last several minutes quietly accumulating positive charge, can no longer remain passive. From the tops of trees, church steeples, radio towers, mountain peaks, and even blades of grass, tiny fingers of positive electricity begin stretching upward toward the descending leader. Scientists call these streamers, and unlike the brilliant bolt that will soon dominate the sky, they are almost completely invisible. Hundreds of them may rise at the same time, each reaching upward through the air, each attempting to become the final connection between the earth and the storm. If you could somehow slow time to a millionth of its normal speed, the scene would look astonishing. The cloud is reaching downward. The earth is reaching upward. It is as though the sky and the ground have been searching for one another all along. Then, in an instant so brief that it lasts only a few millionths of a second, one of those streamers succeeds. The connection is made. Only now does the lightning bolt that we recognize finally appear. The brilliant flash is known as the return stroke, and despite its name, it actually travels upward from the ground toward the cloud. The invisible steppe leader created the path first. The return stroke simply races back along that freshly carved channel at nearly 1/3 the speed of light, illuminating it with an intensity so great that the entire landscape can momentarily appear brighter than daylight. For centuries, people naturally assumed lightning traveled from the clouds downward because that is how it appears to our eyes. But high-speed photography revealed the truth. The path comes first. The dazzling flash races back upward afterward. It is one of those delightful moments in science where reality turns out to be even more surprising than our first impressions. The temperature inside that narrow channel of air climbs almost beyond comprehension. Within less than 1,000th of a second, the air is heated to nearly 30,000 degrees Celsius, roughly 54,000 degrees Fahrenheit. That is about 5 times hotter than the visible surface of the sun. The air has no time to gently warm. It explodes. Molecules that had been drifting peacefully through the atmosphere only moments before are suddenly forced apart with incredible violence. The superheated air expands outward faster than the speed of sound, creating a powerful pressure wave that races away from the lightning channel in every direction. As that pressure wave spreads across the landscape, it gradually slows and softens until it reaches your ears. We call it thunder. Thunder is not a separate event. It is the voice of air responding to impossible heat. The reason thunder often rumbles instead of producing a single sharp crack lies in the incredible length of the lightning bolt itself. A single bolt may stretch for several miles, twisting and branching through different layers of the atmosphere. Sound from the nearest part of the bolt reaches you first, while sound from more distant sections arrives seconds later. Hills reflect it. Clouds scatter it. Valleys echo it. What began as one explosive event becomes a rolling chorus that can continue long after the flash has disappeared. This simple relationship between light and sound gives us one of nature's easiest measurements. Because light travels so unimaginably fast, we see the flash almost instantly. Sound, however, moves through air at only about 343 meters per second, or 1,125 feet per second. That difference allows anyone to estimate how far away a storm is simply by counting the seconds between lightning and thunder. Every 5 seconds corresponds to roughly 1 mile of distance. It is a little piece of physics that countless campers, hikers, and children have quietly practiced while watching summer storms roll across the horizon. Yet even after centuries of studying lightning, the sky still has surprises waiting for us. Not every bolt races toward the ground. In fact, most of them never do. The overwhelming majority of lightning remains hidden inside the storm itself, leaping silently from one cloud to another or between different charged regions within the same cloud. These flashes illuminate the clouds from within like giant lanterns, briefly revealing their towering architecture before darkness returns. From a distance, they appear almost peaceful, soft pulses of white light glowing behind curtains of rain. But inside those clouds, the same incredible temperatures and electrical forces are at work. Sometimes, lightning chooses an even stranger direction. For generations, pilots occasionally reported seeing mysterious flashes shooting upward above thunderstorms instead of downward toward the earth. Their stories were often dismissed as optical illusions because they happened so quickly that almost nobody else witnessed them. Then, in 1989, a low-light camera accidentally captured one. The scientific community was astonished. Towering above the storm, reaching nearly 50 miles into the atmosphere, was an enormous crimson flash unlike anything most researchers had ever seen. Today we know these beautiful phenomena as red sprites. Sprites are among the tallest natural events on Earth, blooming high above thunderstorms in the thin upper atmosphere where the air is so sparse that ordinary lightning cannot exist. They resemble enormous glowing jellyfish, with delicate tendrils hanging beneath brilliant crimson crowns. Most last for less than 1/10 of a second, making them almost impossible to spot with the naked eye. For thousands of years they had likely been dancing above storms completely unnoticed, hidden simply because they occur too high and too quickly for most people to ever see. And sprites are only the beginning. Scientists have also discovered towering blue jets that shoot upward from the tops of thunderstorms, gigantic jets that bridge the gap between clouds and the edge of space, and brief rings of light known as elves that expand across the upper atmosphere at nearly the speed of light. These spectacular displays remained completely unknown until modern cameras became sensitive enough to capture them. It is a humbling reminder that even in the 21st century, our planet still holds secrets hiding in plain sight. Every thunderstorm is far more than a cloud filled with rain. It is an immense electrical engine, reaching from the forests below to the very edge of space, quietly producing phenomena that humanity lived beneath for thousands of years before we even realized they existed. Even stranger than the lightning we see is the lightning we almost never notice. Many people imagine a lightning bolt as a single flash that appears for the briefest instant before disappearing forever. But our eyes are surprisingly easy to fool. The flash seems instantaneous only because it happens faster than our brains can separate its individual parts. In reality, what appears to be one bolt is often several lightning strikes following exactly the same path, one after another, each lasting only a fraction of a second. The channel carved through the air by the first return stroke remains incredibly hot for a brief moment, making it an easy highway for additional surges of electricity to race through. These repeated strokes occur so quickly that our eyes blend them together into the familiar flickering flash we have watched since childhood. A single bolt may contain 3, 4, or even a dozen separate electrical pulses before the sky finally grows dark again. The scale of a lightning bolt is equally difficult to imagine. Some flashes travel only a few miles between cloud and ground, but others stretch across entire states. In 2020, satellites recorded the longest lightning flash ever measured. It extended an astonishing 477 miles, reaching from one end of the southern United States to the other. To put that into perspective, if such a bolt were laid across the ground, it could stretch farther than the distance from New York City to Cleveland, or from Nashville nearly to the Gulf of Mexico. It wasn't a single straight line, of course, but an intricate network of branches weaving through an enormous storm system. For nearly 8 seconds, that vast electrical river remained alive inside the clouds before finally fading away. Nature, it turns out, can draw with electricity on a canvas far larger than we ever imagined. Not all lightning is white. The brilliant flashes we usually see appear white because they are so intensely bright that they overwhelm the color-sensitive cells in our eyes. But under the right conditions, lightning can glow blue, violet, yellow, or even deep crimson. The color depends on several factors, including the temperature of the electrical channel, the composition of the atmosphere it travels through, and the distance between the storm and the observer. Lightning viewed through heavy rain often appears bluish because shorter wavelengths of light scatter differently through water droplets. Bolts occurring near dust, wildfire smoke, or pollution can take on warmer orange or reddish hues. High above thunderstorms, The mysterious red sprites seem almost otherworldly, glowing softly against the darkness of the upper atmosphere like enormous crimson flowers blooming for only a heartbeat. Even the smell after a thunderstorm tells part of the story. Many people notice that the air somehow feels cleaner once a storm has passed. Part of that sensation comes from the rain itself, which washes dust, pollen, and tiny particles from the atmosphere. But another part comes from chemistry unfolding in the wake of every lightning bolt. The tremendous energy released during a strike tears apart ordinary oxygen molecules floating through the air. As those atoms recombine, some form a new molecule made of 3 oxygen atoms instead of 2. This molecule is called ozone. High in Earth's atmosphere, ozone forms a protective blanket that shields life from much of the sun's harmful ultraviolet radiation. Closer to the ground, however, ozone has a sharp, fresh scent that many people instinctively associate with approaching storms. Long before scientists understood the chemistry behind it, people noticed that thunderstorms seemed to leave the air smelling different. They weren't imagining it. They were breathing the subtle fingerprints left behind by lightning itself. But perhaps lightning's most important contribution to life on Earth is one that unfolds completely unnoticed beneath our feet. The atmosphere surrounding our planet is made of nearly 78% nitrogen gas. Every leaf, every blade of grass, every towering redwood, and every flower growing in a quiet meadow depends on nitrogen to build proteins, DNA, and the countless molecules required for life. Yet there is a problem. Although nitrogen fills the air all around us, plants cannot use it in its ordinary form. The 2 nitrogen atoms in each molecule are held together by one of the strongest chemical bonds found in nature. To a plant, the atmosphere is like an enormous pantry filled with food locked inside unbreakable jars. The resource is everywhere, but inaccessible. Lightning possesses enough energy to break those bonds apart. As a bolt tears through the atmosphere, temperatures soar high enough to rip nitrogen molecules open, allowing them to combine with oxygen. Rain then carries these newly formed nitrogen compounds down into the soil, where they become natural fertilizer for plants. Every thunderstorm quietly enriches the earth beneath it, delivering nutrients that forests, grasslands, and crops have depended upon for millions of years. Long before humans invented fertilizer factories, lightning was already feeding the world. Today, scientists estimate that millions of tons of usable nitrogen enter Earth's ecosystems each year thanks to thunderstorms alone. It is one of those beautiful connections in nature that often goes unnoticed. A phenomenon powerful enough to split towering trees can also help nourish the smallest blade of grass. This curious balance between destruction and creation appears again and again throughout the natural world. Lightning certainly has the power to destroy. It ignites wildfires, shatters ancient trees, and occasionally leaves behind glass-like tubes called fulgurites, formed when a bolt strikes sandy soil with such incredible heat that the sand instantly melts. These strange natural sculptures preserve the exact path of the electrical discharge, frozen forever beneath the ground like the fossilized footprints of a storm. Some are only a few inches long. Others extend several feet beneath the surface, branching through the earth just as lightning branches through the sky. Yet the fires sparked by lightning are not always disasters. For countless ecosystems, they are essential. Across vast pine forests, open prairies, and dry savannas, lightning has acted as nature's gardener for millions of years. Periodic fires clear away dead vegetation, return nutrients to the soil, create space for new growth, and even help certain species reproduce. Some pine cones remain tightly sealed with resin until the intense heat of a wildfire melts them open, finally releasing the seeds inside. Without occasional fires, entire forests would gradually change into completely different ecosystems. In this way, the same force that appears violent to us has quietly helped shape the landscapes we now consider natural. It is easy to think of lightning as a visitor, a dramatic interruption to an otherwise peaceful world. But the longer scientists study it, the more they realize something remarkable. Lightning has never been separate from Earth's story. It has been helping write it since the very beginning. As our journey slowly comes to an end, the storm has already begun moving on. The towering clouds that once filled the sky drift quietly toward the horizon, their brilliant flashes becoming less frequent with every passing minute. The thunder that only moments ago echoed across the landscape now arrives as a distant murmur, growing softer until it eventually disappears altogether. One by one, the stars begin returning. The wind grows calmer. The rain eases into a gentle patter before stopping completely. And the earth breathes once again beneath a clear night sky. It is remarkable to think that every thunderstorm is both incredibly familiar and unimaginably complex. From our perspective on the ground, lightning seems almost instantaneous, a brief flash, a clap of thunder, and then it is gone. But now we know that every bolt begins its journey long before that brilliant burst of light. It begins with sunlight warming the oceans, with invisible water vapor rising into the atmosphere, with tiny droplets gathering around microscopic grains of dust, with clouds reaching miles into the sky, with billions upon billions of frozen crystals colliding in complete darkness, with countless electrons quietly separating themselves over the course of many patient minutes. Only after all of that hidden work does the sky finally shine. Perhaps there is something comforting in that. So many of nature's greatest moments are built slowly, quietly, and almost entirely out of sight. The forests that cover our mountains begin as tiny seeds. The rivers that carve vast canyons begin as gentle streams. Stars are born from clouds of dust drifting silently through space for millions of years before they ever produce their first light. Even lightning, one of the fastest and most dramatic events we can witness, is, in many ways, the product of extraordinary patience. Nature is never in a hurry. It simply allows countless small events to build upon one another until something beautiful finally appears. For thousands of years, people looked toward thunderstorms with fear because they did not understand them. They imagined angry gods throwing bolts from the heavens or supernatural forces battling high above the clouds. And perhaps that is understandable. Lightning is one of the few natural events that can instantly transform the world around us. It can illuminate an entire landscape brighter than daylight before disappearing again in less than a heartbeat. It reminds us that our planet is alive, dynamic, and constantly changing. Yet the more science has uncovered, the more extraordinary lightning has become. It is no longer merely a mysterious flash in the sky. It is the story of our atmosphere. The story of water endlessly cycling between ocean and cloud. The story of invisible electric fields stretching across miles of open air. The story of chemistry unfolding above our heads, creating ozone we can smell and nitrogen that nourishes forests and fields. The story of towering storms that reach almost to the edge of space, where crimson sprites and brilliant blue jets dance beyond the limits of ordinary human sight. And perhaps, most wonderfully of all, it is a reminder that our planet still holds mysteries. Even today, scientists continue studying thunderstorms with satellites, high-speed cameras, weather balloons, aircraft, and instruments capable of measuring events that last only millions of a second. Every year, researchers discover something new about storms that humans have lived beneath for our entire existence. There is a quiet beauty in realizing that even something as common as a summer thunderstorm can still surprise us. Sometimes we imagine that science removes the mystery from the world. But perhaps it does the opposite. Every answer simply reveals another, deeper question waiting just beyond it. The more we learn, the more astonishing our universe becomes. Tonight, somewhere on Earth, a storm is beginning to form. Warm air is rising from a sunlit ocean. Tiny droplets are gathering around grains of dust. Ice crystals are beginning their endless dance inside growing clouds. Invisible charges are slowly separating high above the ground. No one beneath that storm can see any of it happening. Not yet. Soon, somewhere in those clouds, an invisible stepped leader will begin searching through the darkness. The Earth will quietly reach upward in return. A path will be found. For just the briefest instant, millions of years of atmospheric physics will unfold in a single brilliant flash. A child may pause at their bedroom window to watch it. A traveler might glimpse it through the window of an airplane. Someone camping beneath a mountain sky may silently count the seconds until the thunder arrives. Most will simply admire its beauty. Now, perhaps, you'll also recognize the incredible story unfolding behind every flash. The invisible journey that began with sunlight, continued through clouds, and ended with one of the most breathtaking displays our planet has ever created. Thank you for joining me on this peaceful exploration of one of nature's greatest mysteries. I hope the next time distant thunder rolls across the horizon, you'll hear it a little differently, not as something frightening, but as the quiet voice of a living planet, endlessly moving water, energy, and light through the skies above us. Until our next adventure together, sleep well. Stay curious. And if a gentle summer storm happens to pass overhead tonight, perhaps leave the curtains open for just a little while. Somewhere beyond those clouds, the Earth is quietly telling one of its oldest stories. Good night.